Okay, so you just learned that the radius of the Earth was the first constant that people found. And not only was it the first one they found, but they found it in 240 BC. It's 2020, 2260 years ago. That's when they came up with an idea as to what the radius of the Earth was. So hopefully you might be geeking out a little bit like I do with this because I just find it almost incomprehensible, inconceivable even, that that long ago we were able to come up with the circumference of the Earth. So I think a lot of times when we're teaching science, we never really teach the history. How do we get to know these things? How do we know the radius of the Earth was? How do we come up with it? Let's do it. So that's going to be the purpose of this activity. So Aristophanes was a Greek mathematician. He was also a geographer and an astronomer. Now, he was responsible for the idea of latitude and longitude, but that's not really what makes him famous. What makes him famous was the fact that he was able to actually calculate the circumference of the Earth. Now, he needed to use, as a mathematician, his geography and his astronomy skills really to be able to figure this out. Now, he knew about Alexandria and Syene. Syene is on the Tropic of Cancer. Now, I've always seen these on a map. I'm going to make this a little bit bigger so you can see it. Tropic of Cancer is here. So Syene is here. Egypt crosses over. So that's where Syene is at. And the Tropic of Capricorn, Tropic of Cancer. And I never knew what they were on the globe. I just know that they were tropics. Okay, never knew what they were. Well, what they are is that during the summer solstice, the Tropic of Cancer is when the sun appears directly overhead. So it's perfectly 90 degrees straight above at its zenith. Now, Syene was actually a little bit north of the tropics, so that's one of our little bit of errors. But when he put a metal stick down, there was no shadow because the sun was directly overhead, so no shadow. Now, he also knew that Alexandria was directly due north of Syene. They were on the same line of longitude. At that exact same time, when the sun was directly overhead, in Syene there was no shadow. In Alexandria, there was a shadow of 7 degrees. That's going to be the key piece of information to figure out the circumference of the Earth. Now, let's just go over a little bit of some basics here. You have a complete circle here, and I broke it up into 4 equal parts. So if this circumference, if it was 8 units long, how long is each part? And likewise, if all of the angles inside a circle add up to be 360 degrees, how big are each of these angles? Okay, so you can go ahead and answer that. Now, circles were very well known to the Greeks. The Greeks were excellent mathematicians. They were also excellent astronomers. The Greeks knew that this ratio of a circumference divided by the diameter of a circle is equal to pi, which is that 3.14 plus a whole bunch of numbers that never end. Just to make you feel better, we're going to put it in the little symbol form. So if I insert a circle, go to shapes, and here we go. I'm not going to put anything on the inside. So the circumference is everything on the outside. The diameter is from one side of the circle through the center directly to the other. That's our diameter. So the radius is 1/2 of the diameter. So if you know the circumference of a circle, you can determine its diameter, which means that you can figure out its radius. Okay, key piece of information, so hold on to that. Now here's a picture of Alexandria and Syene. These are, imagine, the 2 sticks that are pointing into the ground. Now, what we're going to do again, we're going to insert, so make a straight line from each of these two posts to the center of the earth. So we're going to do that. And then one from Alexandria down to the center of the earth. So those two sticks, if they're directly into the ground and straight and flat, they're going to point directly to the center. Okay, they're going to go through a bunch of the earth, but they point directly to the center. So we're going to assume that this little piece is just going to be called R, and this little piece is going to be theta. This is our magic angle, okay? Now it's saying, how can you relate these values to the circumference of the Earth? All right, now, well, we're going to figure that out in just a second. I don't want to get there just yet, okay? Because what I want to do is we want to revisit one other piece of information first. We know that the rays of light coming from the sun were parallel. Now, if the ray of light that hit this post didn't create a shadow, then what that means is if they're parallel from the sun, you will notice now here at Alexandria, now you have a shadow. This is the post, this is the sunlight coming down, that's going to create a shadow. And remember, that angle was 7 degrees. Okay? Now, look at these angles, 1 and 2. Look at this 1 and 2. Look at this 3 and 4. 3 and 4, 1 and 2. Just by looking at it, and yes, we're getting into geometry. We're just not going to tell our kids we're doing geometry. What can you tell me about the angles? What do they look like? Well, hopefully you're saying they look to be like 3 and 4 is the same here. These are the same. These angles are the same. These are the same. These are the same. So if this angle is 7 degrees, how much is this angle? Or if this angle is 7 degrees, rather, that's from the shadow, then this angle has to be 7 degrees. Okay? Now, so we're going to set this up as a ratio. The distance from Alexandria to Syene divided by the circumference of the Earth, we're setting up a ratio, is that theta divided by, and make that a symbol, divided by 360 degrees, because I know that 360 degrees is an entire circle. But we know theta. We know theta is 7 degrees. Okay? So we now have this ratio. The angle between Alexandria and Syene, that's 7 degrees. If I know this distance, I can figure out what ratio it is with the entire Earth. All this is just simple ratios. So now the trick is to figure out R. But here's the thing. They knew that. We have to make a couple assumptions before we go on. The assumption one is that the distance between Alexandria and Syene was 5,000 states. Now, a state, think about it like this. You know, I can say the distance between my house and the university is 40 miles. Well, miles is an arbitrary length. During this time, they use a unit of states. And the distance between Alexandria and Syene was about 5,000. We're also assuming that the Earth was a perfect sphere. Okay? So I want you to figure out some of the rest of these. If I know that one state is 180 meters, how many meters is 5,000 states? And I'm going to give you a hint. It's like saying that one VC or one TV costs 100 is $180. If I want to buy 5,000 TVs, how do you come up with the value? Same thing. One state is 180 meters. How many meters is 5,000 states? Well, think about how you could actually measure, like, how did they get 5,000 states? How could you calculate that distance? I want you to put in the answer before I actually tell you. So pause it, give me an answer. So they knew this because the Alexandria to Syene was a popular trade route, and the military would go this way. Now you've already learned some basic physics in terms of speed. You know, speed is distance divided by time. Soldiers would have to move at a constant rate. If I knew how long the soldiers moved for, if I knew how fast the soldiers moved, I could figure out the distance that they traveled, moving at a certain beat for a set amount of time. So, using this answer as r, what's the circumference of the Earth? And I want you to compare that with the current accepted value of 40,075 for the circumference. And tell me why you think the two are different. So go ahead, I want you to finish this little bit up on your own, turn it in, and hopefully you're going to be just as shocked as I am and surprised and just marvel at the ingenuity of the human brain. Think about it. So I look forward to chatting with you soon, and I hope you will now always know how we calculated the radius of the Earth. Have a good one, and I'll see you next time.